listeners, welcome to the video lecture series on power electronics. In this video, we are going to look into the operation of a buck boost converter with its necessary waveforms. Also, we are going to derive the design formulas for the buck boost converter. For further reading, you can follow this textbook on this corresponding page numbers. The circuit diagram of the buck boost converter is given here. Again, there is a small change in the location of the three elements, that is the switch, inductor and the diode. The capacitor and load are as it is, and the indication of these currents are assumed directions of the current, and this is the assumed direction of the polarity of the output voltage, and this is the input source voltage. And we are going to look into the operation of this converter, and followed by the operation we are going to derive the 14 different expressions for this converter, which is essential for designing this converter. Let us go into the operation of this converter. There are two modes of operation in this converter. One is when the switch is on and the other one is when the switch is off. So now let us look at the waveforms concerned with the gate pulses of this particular switch. I have two modes. One is when the switch is on, other one is the switch is off. T on duration is also called as dt, and T off duration is also called as 1 minus d into t. If I add these two, the total time period of the waveform is t, and dt is the on-time duration of the buck boost converter, or on-time duration of this particular switch. Now let us look into the first mode of operation, that is when the switch is on. If you look at when the switch is on, the current will be circulating in this loop, and this diode will be reverse biased because positive is connected to this point. So this diode will be generally reverse biased. So load will be taken care by the capacitance. So let us see that how the circuit diagram will look like, or equivalent circuit diagram will look like when the switch S is on, SW is on. You can see that this is the place where the inductor and the switch are connected in series, and the inductor is now charging. It is now in the charging mode. If you look at this, diode is in reverse bias, so it does not conduct, and this particular capacitance is responsible for delivering the power to the load. Now if you look at, since the inductance is in the charging mode, there is a linear increase in the inductance current, which is making the inductor current to flow in a linear way. That is from minimum value towards the maximum value. Once it has reached the maximum value, I am going to turn off the switch. Once I turn off the switch, the inductor, amount of energy which is stored in the inductor during the on time of the switch is now in the discharging mode. So this inductor will be discharging to the load via this way because the diode is in the reverse bias. Now you can see the more equivalent circuit when the switch is in off condition. You can see that now the energy which is stored in the inductor when the switch is on is now discharging. So the current will be circulating in this way, and it will be circulating in the direction what I am showing in my mouse. Very important, these indications of the current direction are the assumed direction. Actually, the inductor current will be circulating only in the counterclockwise direction. Since during this mode of operation, the inductance is discharging, the energy stored in the inductor is discharged to the load, the amount of current will be slowly decaying as it is indicated here. Slowly the amount of the current will be decreasing from maximum value to minimum value. Once it has reached this point, again I am going to turn on the switch, so which makes the inductor to charge again. So the inductor current will slowly increase from minimum value to maximum value. Once it has reached its maximum value, again I will turn off. Again the inductor will slowly discharge. So the inductor current is increasing from minimum value to maximum value whenever the switch is on, and it is decreasing from maximum value to minimum value whenever the switch is off. So this let me write this as IL minimum, which is the minimum value of the inductor current, and this is IL maximum, which is the maximum value of the inductor current. Again I repeat, the indications of these three current directions are the assumed directions. Now the average value of the inductance current will be somewhere in the middle of this, which is something like this, what I am drawing here. So this is the average value of the inductor current. So let me write this as IL average. So this is how the buck boost converter operates. Now let us go and derive the design expressions related to this buck boost converter. Let us try to calculate the inductor voltage and capacitor current when the switch S is on and switch S is in off condition. So let us first try to write when SW is in on condition. Let us try to write the expressions for VL on, that is the on voltage of the inductor and the current through the capacitor when the switch is in on condition. Let us try to write the expressions for these two. Now the switch is on condition. So if I look at this condition, let me try to represent this. So this is the positive and this is negative, and the voltage across the inductor, let it be VL. So there will be a current which is circulating inside the loop, something in this direction. So when I try to write the Kirchhoff's voltage law expression for this loop, I can write Vs, which is the potential rise. You can see that the current direction is moving from negative to positive, whereas if it is looked at the inductor voltage, it is moving from positive to negative. So Vs is equal to VL. So VL on is nothing but Vs. So this is the expression number 1. Similarly, when I try to write the Kirchhoff's current law equation at this particular node, I will get, since this diode does not carry any current when the switch is on because it is in the off condition. So let me try to apply Kirchhoff's current law for this particular node. ID is equal to 0. So IC plus IC plus IO, that is load current, IC plus IO will be equal to 0. So this means that IC on is equal to minus I0. So this is the first two expressions that we get from the when the switch is in on condition. Condition number 2 is, or the mode of operation, second mode of operation is when the switch is in off condition. When the switch is in off condition, the circuit will behave something like this. If you look at the capacitor voltage, since this is positive and this is negative, this is the assumed polarity of the load voltage. So this is also considered to be positive and this is considered to be negative, and let this voltage be V0 because both are same, or VC, whatever we call. Since the current from the inductor will be discharging to the load only in this way, so this is the direction of current which is circulating inside this loop. So once I try to write the Kirchhoff's voltage law equation for this loop, that is point number 2, when the switch is in off condition, when the switch SW is in off condition, let me try to write the expression for the Kirchhoff's voltage law for this loop, that is KVL here. If I try to write this, if I look at this current, this is potential drop, VL is potential drop, whereas this is a potential rise. So VL is equal to V0. So if I try to write it in the off condition, VL off, that is the voltage across the inductor when the switch is in off condition is equal to V0. So this is the third expression. Similarly, if I look at the current, as I told already that the current through the inductor is this, which is flowing in this direction, and this IC will be flowing in this direction, and this I0 will be coming and it is coming in this direction. So if I try to write the Kirchhoff's current law equation for this loop, this node, that is at this particular node, I can write, if I try to apply KCL at this particular node, I mean to write at this particular node, I can write IL plus IC plus I0 is equal to 0. All the three put together is equal to 0. So I need IC under off condition. So IC under off condition can be written as minus of IL plus I0. So this is the fourth expression that is of our interest. So let me write all these four expressions in this corner for further easy derivation of my continuing derivations. So I have written all these four equations in this corner for further easy derivation. And now the next topic of derivation is to derive the expression for volt second balance and current second balance. So let us try to derive these two. So let us try to derive the volt second balance. So volt second balance in the sense VL on into T on plus VL off into T off. So I am going to take these two, VL on into T on plus VL off into T off is equals to 0. So VL on is Vs, which is from the expression 1. T on is, here it is given dt. So VL on into T on. T on is dt plus VL off. VL off from expression 3 is V naught, and dt, T off is 1 minus d into T. 1 minus d into T. So this is T off, which is equal to 0. This is what the meaning of volt second balance. So let us simplify this expression. So we'll get Vs into dt plus V naught into T minus V naught into dt. So this is equal to 0. So further simplification, I think this step itself it is not required. Directly from this expression, I can write V naught into 1 minus d into T is equals to minus Vs into dt. Minus Vs into dt. So from this, I will get V naught is equals to minus Vs into dt whole divided by 1 minus d into T. So this T and this T will get cancelled out, left out with V naught is equals to minus Vs whole into d whole divided by 1 minus d. So this is the expression for the output voltage of an buck boost converter when it is supplied with the input voltage of Vs and if it is operating with a duty cycle D. Very important to be understood here, if you look at it is a negative voltage. What this means negative? The assumed voltage polarity is this is positive, this is negative. Since it is negative, it is opposite to that. Meaning is this side is positive and this side is negative. So actually the assumed polarity is this is positive. Why I assumed this as positive? Because in the previous two derivations we assumed this as positive. The same thing has been continued here in order to understand or in order to explain the concepts easily. But actually the polarity of the buck boost converter is this is positive and this is negative. Similarly, when I try to substitute D is equals to 0 here, if I substitute D is equals to 0, my output voltage V0 becomes 0. When I substitute D is equals to 1, the denominator becomes infinity. So the denominator means it becomes infinity in the sense V out will be, theoretically the output voltage is infinity. When I put D is equals to 0.5, I can say that when I put D is equals to 0.5, V0 is equals to 0.5 in the numerator, 1 minus 0.5, again 0.5 the denominator, both 0.5 will get cancelled. So the output voltage will become minus Vs, which means that the output voltage can be varied from 0 to infinity based on the duty cycle. That is, it acts as a buck converter as well as it acts as a boost converter. Between 0 to 0.5, it acts as a buck. From 0.5 to 1, it acts as a boost converter. This is what one of the important understanding of this buck boost converter. The other name of this buck boost converter is step up down converter. The next part is we are going to derive the expression for current second balance. So if I try to derive the expression for current second balance, then I have to take these two expressions, that is expression number 2 and expression number 4. That is, I am going to multiply IC on, that is minus I0 into the on time of the switch, that is dt, minus of IL plus I0, that is IC off, IL plus I0 into 1 minus d into t, which should be equal to 0. So this is the simple expression. So let me try to simplify this expression. Minus I0 into dt, minus I0 into dt, minus IL plus I0 into t, minus IL plus I0 into t, minus minus plus, plus IL plus I0 into dt is equal to 0. Simple simplification. So again further I can simplify this. This becomes I0 into dt minus IL into t minus I0 into t plus IL into dt plus I0 into dt is equal to 0. So if I look at this I naught into dt and minus I naught into dt will get cancel each other. So finally left out with minus IL into t minus plus IL into dt. I'll take the third expression IL into dt, which is equal to, this side I will bring this becomes I naught into t. So I can rewrite this expression as I naught into t is equals to, if I take IL into t as common, minus IL into t as common. So sorry, this if I take this side as IL into t as common, this becomes minus 1 minus d. So I can take minus common, I minus IL into dt common. So plus 1 minus d into t. T is already there. So this t and this t will get cancelled. So finally I naught is equals to, so from this expression I will get IL is equals to minus I naught whole divided by 1 minus d. So this is the expression for the average value of the inductor current. Average value of the inductor current is denoted by this red line, and this I can write it as modulus value of this can be taken. So I naught divided by 1 minus d is the expression for this average value. Now from this expression we can understand this inductor current is opposite to that of the direction of I naught what I have assumed. If I look at, this is the direction of I naught I assumed, but the inductor current is opposite to that. So it is evident that the inductor current is flowing in the anti-clockwise direction. So this is the next equation which is needed for us for design purpose. So let me take these two equations and put it in this corner for further simply making the derivation simple. So I added these two equations in this corner for further easy understanding. So the ripple in the inductor current can be easily found out by the similar method which we have followed for the previous two derivations. That is, let us try to write the expression 1, that is VL on, that is when the switch is on, which is equal to Vs. The switch is on, which is equal to the voltage across the inductor is given by Vs. That is from the expression 1. We know that the inductor voltage can be written as L into, this is happening during the on time of the switch. So this can be written as V into di on divided by dt on, which is equal to Vs. We already seen in the previous two derivations, the ripple current is nothing but this value. This is what I call it as delta IL. This is delta IL. And if I look at this part alone, it is called as, this is half of this, so delta IL by 2. And this part is another half, so this is another delta IL by 2. So if I look at, during the on time, the current is varying from minimum to maximum, which is what we call it as delta IL. So this dt on can be written as L into delta IL, because the current is varying from minimum to maximum, which is equal to delta IL. This is happening during this period. That is change in current. This is what I call it as change in current. Within this duration, the duration is from 0 to dt. So dt on is nothing but divided by dt, which is equal to Vs. It's a very similar thing which we have followed in the previous two derivations. So from this, let me calculate my delta IL. Delta IL is equals to Vs into dt divided by L. Vs into dt divided by L. This can be further be simplified as Vs into d divided by L, and this t can be written as 1 by f, so this comes in the denominator. So the expression for the inductor current ripple is Vs into d by Lf. So this is the next expression, which is expression number 7 of this derivation. The next part of the derivation is to find out the maximum inductor current and minimum inductor current values, that is ILMAX and ILMIN. Let us try to derive these two. So the sixth part of the derivation is to find out the maximum value of inductor current. maximum value of inductor current can be found out by IL average plus IL maximum. So I can write IL max as IL average, that is the average value of the inductor current, plus delta IL by 2. So this part, so IL average plus delta IL by 2. So this is the expression for the maximum value of the inductor current. Now you can substitute this IL average with I0 divided by 1 minus D, and this I0 can be replaced by V0 by R, as if the load is of resistive in nature, and you can play with this expression. Similarly, the minimum value of this inductor current, that is IL minimum can be written as IL average, that is the average value of the inductor current, minus this part, that is minus delta IL by 2. So this is the 6th, 7th, 8th and 9th expression of our interest. So these two expressions denotes the values of expressions for maximum value and minimum value of the inductor current. So the next part of the derivation is to find out the source current. So let us try to derive this. So 8th part of the derivation, to find out source current, what we had did in the previous two derivations, same thing I am going to follow. That is, the input power is equal to output power. We are going to put input power is equal to output power. Input power is Vs, that is supply voltage, into the source current. So source voltage into source current. Here both are same. This is the source current, which is equal to V0 into I0. So from this, if I try to find out the value of the supply voltage current, which is equal to V0 into I0 by Vs. V0 into I0 by Vs. Now you can replace this V0 with expression 5, and you can play with this expression. And similarly, you can replace this I0 by V0 by R if the load is assumed to be a resistive load, and all this can be done easily by putting the appropriate expressions on all these expressions. So this is the next expression which is of our interest. So this is the 10th expression. So 7, 8, 9, 10. These 4 expressions, again I am going to write it in this corner for making the further derivations so simple. I have written all the derived expressions so far in this corner to make the further derivations so simple. With this, let me conclude this buck boost converter video session, and again the remaining part of the buck boost derivation will be carried out in the next video. Thank you for your patient listening. Thank you.